Thank you for your attention to our work and CBM-HNMU introducing a framework to modify black box models to improve interpretability and accuracy through human-understandable conceptual interventions. The main contributions are: first, an integrated explanation framework, combining attribution with explanations based on multimodal concepts. Second, going beyond sample-level automatic intervention, automatically discovering confusing concepts based on global gradient contributions and maintaining non-interference class predictions. Third, unlabeled human-machine mutual understanding, an unsupervised concept communication module combining CBM and NMF. Next, let's move on to the introduction of the method framework. As shown in the figure on the right, CBM-HNMU is divided into 3 steps. Step A. Local approximation. The CBM inference structure first distills an interpretable basis that approximates the original black box model's class predictions on confused classes, gamma. Step B. Concept intervention. Next, the classification bias is corrected by intervening with concepts that are detrimental to the decision-making and selected based on the concept score of SNT and SPF in the CBM obtained from Step A. Step C. Knowledge transfer. Finally, the corrective adjustments made to the CBM in Step B are transferred back to the black box model to improve reasoning and reduce biases. More detailed, as shown in the figure on the right, confusion category pair selection. A specific number of confusion categories are selected based on the confusion matrix of the model on the validation set. Then, Step A will use the concept bottleneck to take the black box model hidden features as input and category prediction as output, combined with knowledge distillation, to locally approximate the black box model reasoning process on the selected confusion category. After obtaining the approximate concept bottleneck structure, Step B screens out concepts that have a negative effect on true category prediction according to the concept scores SNT and SPF based on the global gradient contribution and intervenes to obtain the intervened concept bottleneck model. The detailed calculation process of SNT and SPF is shown in the formula on the right, and the specific calculation process is shown in Algorithm 1. Finally, Step C uses the joint prediction obtained by concatenating the intervened concept bottleneck model and the frozen copy of the original black box model as the teacher, and the prediction of the original black box as the student to perform reverse distillation and transfer error correction knowledge. To verify the effectiveness of the proposed method framework, we conducted extensive experiments on multiple datasets and model architectures. First, we verified the improvement in generalization performance and the error correction effect of erroneous samples after using CBM-HNMU to intervene in the black box. As shown in Table 1, the 3 architectures in our experiments achieved global accuracy improvements across 5 datasets after intervention with CBM-HNMU. To further verify the effect of CBM-HNMU, we conduct the identical comparative test using another 3 architectures on Flower 102, FGVC aircraft, and CUB-200. The results are presented in Table 2. Table 3 shows the most corrected samples in test are related to the intervened classes, either because they were previously predicted as one of the confusion classes or because their true labels belong to the confusion set. In the next, we analyze how the intervened black box's performance improvement relates to changes in natural language and visual-related concepts. We observe that intervened natural language concepts often shift related black box visual concept explanations. For example, as shown in Figure 1 on the left, based on SNT and SPF, we intervened on concepts like T-shaped tail, ultimately correcting the model's incorrect prediction, MD80, was changed to MD87. Consistently, the importance score of the tail visual concept, which matched the intervened natural language description, also decreased after the intervention. This demonstrates that CBM-HNMU does more than just transfer knowledge, but proactively corrects black box errors by coordinating human and neural network reasoning. Furthermore, we used user study to verify that the conceptual intervention of CBM-HNMU is consistent with human visual perception. We tested whether the concepts suppressed by CBM-HNMU are the same cues that humans find misleading. 30 paid, non-expert volunteers examined each exemplar along with its intervention concept and scored the concept as I, true class Q, CT, 2, false class Q, CF, or 3, a semantically related Q shared by both classes, CR. The result shown in Figure 4 indicates that CBM-HNMU targets exactly the visual hints that mislead both the network and human observers, validating the choice of intervention concepts. Finally, we conduct extensive ablation experiments to ensure the necessity and effectiveness of the method module. As shown in the picture above, A1 helps select the optimal number of intervention, confounding, categories to ensure higher intervention benefits, A2-3. Further demonstrates the effectiveness of the proposed method. A 4-5 proves that the local approximation module can support effective generalization, A6. Further demonstrates the universal alignment of intervention concepts and human visual perception. This concludes our introduction to intervening in black box concept bottleneck models for enhancing human neural network mutual understanding. For more details, please refer to the original paper and visit the project homepage. If you have any questions, please contact the author or leave a message in the project repository.